Good morning, I am Dr. Ohlhoff and I will be presenting the second lecture on Chapter 4, which is on optimization theory. In our first lecture, we discussed local minimum and local maximum points of a function, critical points and saddle points. We also found a method to classify the critical points of a function as local maximum or local minimum points or saddle points. In this section, we will be discussing global extreme values of a function of two variables. Here are the definitions. Our first definition is for the notion of a global minimum. This definition states that a function f attains a global minimum at a point in its domain if the function value at that point is the smallest of all the function values of the function over the entire domain. The second definition is for a global maximum, and this definition says that a function f attains a global maximum at a point in its domain if the function value at that point is the greatest of all possible function values of the function taken over the entire domain of the function. We can now reformulate Theorem 111 as follows. The theorem states that a continuous function defined on a closed and bounded set will attain a global maximum and a global minimum on that set. Can you see that this is similar to the theorem for a function of one variable that stated that a continuous function on a closed interval will attain a global maximum and a global minimum? Of course, it is very useful to know that a function attains a global maximum and a global minimum. But how do we find these points where the function attains its global extremes? Let's see what we can do. Theorem 120 will help us to find the global extremes of a function. This theorem tells us that if f attains a global maximum or minimum at a point AB in its domain, then that point AB is actually a local maximum or minimum point of the function. The proof of this theorem follows directly from the definitions. For example, just remember that if f attains a global maximum at the point AB, then the function value at AB is greater than or equal to all of the other function values of f. That then also means that the function value at AB will be greater than or equal to all of the function values of f in any neighborhood of the point AB. Thus, the point AB will be a local maximum point of the function f. Here is an important corollary to Theorem 120. Corollary 121. Let f be a function of two variables with domain D, and assume that f attains a global minimum value on D, denoted by min subscript f, and f attains a global maximum value on D, denoted by max subscript f. Further, let E be the set consisting of all the points in D that are either local maximum or local minimum points of f. Then the global minimum of f is the smallest of all the function values of f at each of its local maximum or local minimum points. And the global maximum of f is the greatest of all the function values of f at each of its local minimum or local maximum points. Let's prove the second part of this corollary. Suppose f has its global maximum value at the point PQ in D. It then follows that the global maximum of f is equal to the function value of f at the point PQ, and that is greater than or equal to all the other function values of x with xy in D. In particular, it follows that the global maximum of f, which is the function value of f at PQ, is also greater than or equal to the function value of f at any point that is a local maximum or a local minimum point of f. But by theorem 120, the point PQ is also a local maximum point of f. That means the point PQ is also an element of E, which is the set of all the local maximum and minimum points of f. Since the function value at PQ is greater than or equal to the function value at AB for any point AB in E, and since the point PQ itself is also an element of E, it now follows that the global maximum of f is indeed the maximum of the set of all function values at points AB that come from E. That concludes this proof. Corollary 121 tells us how we can go about to find the global extreme values of a function. The first thing that we need to do is to find all the points that are local maximum or local minimum points of the function. The global maximum value of f is then the greatest of the function values at each of these local extreme points that you find in the first step. Likewise, the global minimum value of f is the smallest of all the function values at the local extreme points of f, that is, at the points that you found in the first step. Corollary 113 also gives us a further clue as to how to find the global extreme values of a function. According to Corollary 113, the only possible local extremes of a function are either at critical points, or singular points, or points on the boundary. But how do we go about to identify local extreme points of a function on the boundary? Well, here is a theorem that tells us what to do. Theorem 122 assumes that we have a function f of two variables defined on a closed set D. Furthermore, it is assumed that we have a curve that forms a part of the boundary of D, and that curve can be represented by a continuous function of one variable defined on a closed interval. The theorem now states that if the point PQ on C is a local extreme point of f on D, then the function h, which is a function of one variable, with h at x equals f at x comma g at x, with x element of the closed interval CD, has a local maximum or minimum at the point P in the closed interval CD. We note that if the point PQ is a local extreme point of the function f, then P is a local extreme of some function h of one variable. So, to identify local extreme points of f on the boundary, we need to identify local extremes of this function h of one variable. We will not prove this theorem, but let's do some examples to apply the knowledge we've gained so far. In this example, D is the triangular region with vertices at 0, 0, 1, 1 and 2, 0 indicated in the sketch. The function f that we considered, defined on D, is given by f at xy equals x squared minus 4xy plus 2y. In order to find the global extremes of f on D, we first find the critical points. For that, we need the first derivatives of f, which I have shown there on the screen. The critical points are where both the first derivatives are equal to 0. So we need to solve the simultaneous equations 1 and 2. We can see from the second equation that x is a half, and if we substitute a half for x in the first equation, we find that y is a quarter. Therefore, the only critical point is the point a half, a quarter. A word of caution is necessary at this page. As you can see, the expressions for the function f as well as the expressions for the two partial derivatives, are valid for all real numbers x and y. That means that the points where the partial derivatives are both zero may yield a point that is not within the domain of the function that was given. So we need to convince ourselves that this critical point that we found is indeed in the set D. We note that the point xy is in D if either x lies between 0 and 1 and y lies between 0 and x, or x lies between 1 and 2 and y lies between 0 and 2 minus x. Since a half clearly lies between 0 and 1, and a quarter clearly lies between 0 and the value of x, which is a half, it follows that the point a half, a quarter, is indeed in D. We know that to find the global extremes of f, we need to find critical points, singular points, and we need to consider boundary points. Since the first order derivatives exist everywhere, there are no singular points. For the boundary points, we need to consider the three curves that make up the boundary of D. Let's name them C1, C2, and C3. In the context of Theorem 122, you can see that on C1, y is equal to 0, and x lies between 0 and 2, and we have the function h1 defined by h1 at x is equal to x squared, with x between 0 and 2. To find the points where the function h1 possibly has a local maximum or minimum, we find the first derivative, which is only 0 when x is 0. We know that a function of one variable defined on a closed interval attains its extreme values either at the critical points or at the endpoints of the interval. Therefore, the only possible points where h1 attains an extreme value are at x equals 0 and x equals 2. We can now conclude that the only points on C1 where f can possibly attain an extreme value are at the points 0, 0 and 2, 0. Now let's see what happens on C2. On C2, we have y equals 2 minus x, with x between 1 and 2. Therefore, the function h2 in the context of Theorem 122 ends up being equal to 5x squared minus 10x plus 4, with x between 1 and 2. To find the points where h2 possibly attains an extreme value, we need to find the critical points, and we need to consider the two endpoints of the interval. As you can see, the only points where h2 can possibly attain an extreme are when x is 1 or x equals 2. Since the possible extremes of h2 are at x equals 1 or x equals 2, it follows that the points on C2 where f possibly attains an extreme value are the points 1, 1 and 2, 0. We follow the same procedure to find the points on C3 where f can possibly have an extreme value. You can follow the calculations in the lecture notes. We have now gathered all the points that we need to consider where f can possibly attain an extreme value. Those are the critical point and the points that we found on the curves C1, C2, and C3. All that remains is to calculate the value of the function at each of these points. The global maximum is then the greatest of these function values, and the global minimum is the smallest of these function values. You can check the answers in the lecture notes. Example 124 is given as self-study. That concludes this lecture. Goodbye and good luck.